What is the most distant object we can see in the solar system? Do satellites collide? And how come we have pictures of the Milky Way? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down and I will gather them up and I will answer them here. All right, let's get into the questions. Thomas Kluza, 3663. What is the most faraway object currently observed going around the sun within the solar system, which has a distinct name, and how far is it? What telescope or spacecraft observatory has found it, and was it the actual limit? Astronomers have discovered many objects in the outer solar system, out in the Kuiper belt, that I think are going to meet your needs. So I'm just going to give you like the direct answer to this, and that is the most distant object in the solar system that's ever been seen by astronomers is an object named 2018 AG 37. And its nickname is called Far, Far Out. And it's named because there was another object called Far Out that was thought to be the most distant object, and then Far, Far Out superseded that, and so now that is the most distant object that we know of. And I guess now this is the rule, and so when the next object is found, it has to be called Far, Far, Far Out, and we just keep adding fars forever. So Far, Far Out was observed at 132 astronomical units. And just for comparison, Pluto is at about 50 astronomical units, so it is much farther than Pluto. And it's not a small object. It is probably in the dwarf planet class. It's an object that's about 400 kilometers across, so it's probably going to be roughly spherical, and is a pretty substantial object. Now, it was found using the Subaru telescope, and this is an 8.2 meter telescope that's located on Hawaii. It's only been observed about 9 times in the entire history that astronomers have known about it. And so far, that record has yet to be beaten, but it will be destroyed when Vera Rubin comes online next year. So to stay tuned for that, when we just suddenly have just an enormous number of new objects that have been found. Now that said, I want to sort of talk about a couple of other kinds of objects that are similar and are interesting in their own ways. So one is the dwarf planet Sedna. And this is an object that would be the most distant object if it was at the farthest point in its orbit, because it is on a 10,000 year orbit that brings it between about 76 astronomical units. So, about 50% farther away than Pluto, but then goes all the way out to almost 1,000 astronomical units. It does this big, long elliptical orbit. And astronomers found it as it's approaching that closest point. So it's just a fluke that was found on that 10,000 year orbit. But these are nothing compared to the long period comets that we see falling into the solar system. These are on orbits that take 30 million years or more. And so the most distant long period comet that's ever been seen probably has, like at its greatest distance from the sun, is about 0.4 light years. And so it just falling into the solar system for hundreds of thousands, millions of years until it finally passed by the sun for the first time. Or sometimes it just fall directly into the sun, and that's that, which is kind of depressing. And so this Oort cloud is thought to go about halfway to the closest star. And there's almost certainly going to be large objects out there in that Oort cloud. So, what is the most distant object in the solar system? We have no idea, and we will never know. Now, you might have noticed the Star Trek planet name that appeared above my shoulder. This is a way for you to vote, for you to tell us what you thought was the most fancy striking question of the week. And so the winner this week was for Ryan about dark matter. Is it only observed at the farthest reach of the universe, or is there dark matter closer? So thank you, Ryan, for asking the question. Thanks everybody for voting. Now, we're going to give a different Star Trek planet name beside each one of the questions this week. We'll put a list of them down in the show notes down below, as well as the chapter markers. And so just when you post a question or a comment or anything, just include the code word for the planet name for the question that you thought was the best. And then we will count them up and we will celebrate that here. Jared T. Brush, why don't satellites ever collide? Is there a public place to know the directions of satellites? What if I want to put a satellite into space and not tell anyone its direction? Is that illegal? Who says satellites don't collide? satellites have collided. In fact, less than 10 satellite collisions have been found in space so far. And there's been a couple of high-profile collisions. Probably the most famous one was in 2009. An Iridian satellite, this was a telecommunications satellite, fully functional, was smashed into by a Russian Cosmos 2251 satellite. And this one was inoperational. It's a piece of space junk. And smashed into the Iridium satellite, destroyed it, and generated thousands of pieces of debris. And in fact, the space tracking agencies are still tracking hundreds of pieces of debris. But it was thought that there was about 2,000 pieces of debris that were larger than several centimeters across. So it was pretty significant. And in fact, it was so significant that one of the pieces of debris came so close to the International Space Station, came within about 120 meters of the International Space Station, that the astronauts on board had to go and hide in the Soyuz capsule and be ready to evacuate if the debris actually got closer to that. And there are times when ISS has to change its orbit slightly because there's a piece of space debris or there's a warning. And, it's believed that every day several satellites come within a kilometer of each other, but they probably come a lot closer than that. People have seen instances of satellites coming within tens of meters of each other. And this problem is just going to get worse. As there are more satellites launched into space, you've got more chances of these close flybys. Now, your question was, is there a public place to know the directions of satellites? Yeah, there's a bunch of online websites that you can go to be able to track the positions of various satellites. So the one that I like is Heavens Above. They've got really prominent locations for the International Space Station, as well as various spacecraft that are launched, Hubble Space Telescope, things like that. But they've got data for as many satellites as you can possibly imagine. And you can just go and see, it'll show you where you are, and you see all the satellites are going to be flying overhead. In many cases, if you go outside and you see a satellite flying overhead, you can go back, look at Heavens Above, and you can know what that satellite was. For the third part of your question, what if you want to put a satellite into space and not tell anyone? Is that illegal? Well, you can't, because you have to launch the satellite. And so you're going to launch the satellite on a SpaceX rocket. You're going to launch it on a Russian rocket. You're going to launch it on a Chinese rocket. It's obvious that you have launched that rocket, and there are many people that are tracking the launches of rockets for obvious reasons. And so then the direction and trajectory of your satellite is then very well known. Now, are there any rules to stop you from launching your rocket? And the answer is not internationally. So there are going to be rules for a specific country. Like if you are a US citizen and you want to launch it on a US rocket, there are rules. You can't just launch it willy-nilly. You can't just have it broadcasting across different spectra. You've got to, there are various rules that you have to be willing to adhere to. But there are no international rules that absolutely define where you have to launch your satellite to. And this is a big problem, right? Like because we have no international regulations that define where satellites should be launched, what kinds of orbits they can use, we have this problem with space junk. We have this problem with satellites that are getting really close to each other. So hopefully someone will solve this problem. There will be an international agreement that will come together and will define where satellites are allowed to be launched, like the way airplanes fly along corridors, the way boats sail along corridors so they don't collide with each other. We need that for space. Pissed Off Christoph, where do pictures of the Milky Way come from? One of my favorite things to take pictures of is the Milky Way. And you can absolutely take images of the Milky Way. All you have to do is go out in a place with relatively dark skies and take a long exposure image with your DSLR camera. And even modern smartphones can do this now. I have a Pixel 6 and it has a really good astrophotography mode. If you put it into a mode where if you put it on a tripod and so it remains really still, then it will shift into astrophotography mode and it will take a pretty good image of the Milky Way. It'll show you the dust lanes and that. Now, obviously, we are trapped inside the Milky Way. And so all of the images that you're going to see of the Milky Way were taken from planet Earth. This is the only place that we can actually take images of the Milky Way. And yet, obviously, we have seen images of what the Milky Way looks like And the reality is that we don't know exactly what the Milky Way looks like because we're inside. It is the equivalent of you not knowing what the outside of your house looks like if you are inside your house. Now, but you could get glimpses, right? Imagine cars driving past, and you could see a little reflection off the window as a car goes past, and you get a little bit of an idea like, oh, the outside of my house is blue. Okay, all right, I'm going to paint my house blue. And I sort of know the shape of the house from the inside, so I can probably guess what the shape of the house to the outside is, but I don't really know the siding and all that kind of stuff. And so we have ways of being able to measure the rough structure of the Milky Way. And there's a couple of really useful tools. One is pulsars. So these are dead stars, neutron stars that are spinning really rapidly. They're putting out pulses, and we can see them for a very long distance away across the Milky Way. And if you observe enough of these pulsars, these beacons, you start to get this sense of what is the larger structure of the Milky Way. And then we have missions like Gaia, which are tracking the location and direction of billions of stars in the Milky Way. And so in that, we are able to just get this sense of what is the nearby structure of the Milky Way and sense some of its larger structures. Like, does it have a bar at the center? Does it have 2 spiral arms, 4 spiral arms, things like that? And then when you've sort of got this rough sense of what the Milky Way probably looks like, well, then we've got a universe of other examples of spiral galaxies that we can look at and then try to compare what we know about the Milky Way to what's out there. And you can just shop around until you find a galaxy that is nicely face on, that is a really good model of what our Milky Way looks like. And plenty of these examples. You'll see images from the Hubble Space Telescope where you've got a galaxy that is a face-on spiral, and astronomers consider it to be a near twin of the Milky Way. We don't know exactly what the Milky Way looks like, but it's pretty close to this galaxy or that galaxy. And really, until we're able to send a spacecraft hundreds of thousands of light years away to be able to get up above the disk of the Milky Way, will we ever be able to actually get an image and take a photo of the Milky Way from outside of it. So until then, we have to just theorize what it probably looks like. Use our imagination and science. Taryn Pulikanti, do you think that astrophotography as a hobby can be turned into something serious? That's a tough question. So you might not know, but I am my father is a professional photographer. So on the small island that I grew up on, my father was kind of like the historian of the island, but also took portrait photographs, also sold all his photographs to the local newspaper, also did art shows where he sold photographs to rich art collectors in Vancouver, and also had his photographs published in various books. And so I know from personal experience what it was like to grow up in a household where my father's income was coming from being a professional photographer. Now, there were lines that he wouldn't cross. Like, he just got sick of doing wedding photography. He got sick of doing portrait photos for people when they wanted it done. Like, he would take photographs and he would do like street photography and things like that. But he sort of had his limits, and that limited his financial return. We were poor. For sure. And he also had to make money driving a backhoe and doing other, carpentry type jobs. So I think, it's always been incredibly difficult to make a living being a photographer. You're an artist. And I think the same thing goes for doing astrophotography. Like, if what you want to do is only be an astrophotographer and have that be your living, I don't think that's possible. Like, there might be a couple of people who have Patreons who are selling their photos or the rights to their photos for the covers of various magazines, or they do art shows and they're successful. There's going to be a handful across planet Earth, but it is not a super viable form of revenue. And I think that's fine. Like, I think that there are certain things that can just remain hobbies. And as soon as you try to make money from them, then it can pollute your enjoyment of the hobby itself. I think astrophotography is one of the most rewarding hobbies that I can think of as it relates to astronomy. I mean, it's so great. You are setting up this telescope. You are observing photons that are coming from space. You are putting in different kinds of filters. You are choosing how long you want to do your exposures. You're thinking about objects in the foreground and the background. And you are then working in Photoshop to try to bring out various parts of the image, while at the same time trying to maintain the raw data that came your way. It's a fascinating bottomless hobby with a ton of variables. And those are the best kind, right? The ones that are relatively straightforward to get into, but are infinitely complex as you really start to plumb the depths of them. So I think if you want to get into a hobby of astrophotography, I think that's wonderful. And I highly recommend it. You know, just try to limit the rabbit hole, try to limit how much you spend on the hobby. The top piece of advice that I have for anybody who is really interested in getting into astrophotography is that you can save yourself a ton of pain and money by learning to do the image processing first. So instead of going out and buying a $10,000 telescope or a $5,000 telescope and then taking raw data and then trying to make those images look really good, what you should do is learn how to work with the images themselves. And there's unlimited numbers of images from the Hubble Space Telescope. You can go to the Hubble Space Telescope data archive. You can download images on any object that you can imagine that nobody has ever tried to present artistically because it was used scientifically. And you can just learn how to bring from the raw data format, the FITS format that astrophotos are taken in, bring them into Photoshop, separate out the layers, change the contrast, sort of work with the image to try and really bring out the best version of it. This is what Judy Schmidt does, and she is often seen as a collaborator on dozens of very famous astrophotos, lots of press releases from NASA. They'll give credit to Judy Schmidt. She's fantastic. And once you've built up those skills on working with the raw image data, and you're still into it, then get a telescope. Then start taking your own data where you're getting images of the things that you want to do. Because I promise you, like if you get into this, you will reach this brick wall where you're taking these images and you don't like them because your limiting skill is the data processing. And so you'll take these images, the raw data is in there. Judy can make your images look amazing, but you don't have the skills yet in the processing side. But if you practice the processing side, get really good, it's all free. I mean, okay, you need access to Photoshop, you can use GIMP or whatever. And then when you feel like you're really good at processing images from the greatest telescopes that have ever been built, James Webb, Hubble Space Telescope, the Very Large Telescope, you can work with that data, then come back around and get your own telescope and then start taking your own pictures. So you can really get into this hobby and get really good at it without spending any money, which is amazing. If you want to support the work that we do at Universe Today, why don't you consider joining our Patreon club? Now, I sort of talk about the paid patron members, but I want to remind you that you don't have to be a paid Patreon member. You can be a free member as well. You can subscribe to us on Patreon totally for free. Then you'll get notified whenever any of the new videos and stuff that we release goes live. Often we just release it at the same time. And the cool thing about that is there's no ads. So if you watch our stuff on Patreon, there are no ads. And you know that you're not going to lose our videos in the shuffle of the YouTube subscriptions. You're not beholden to some algorithm. You'll get a notification whenever we release a new video, and it's completely free. Now, obviously, my hope is that you will watch all of this amazing content that we're releasing and think about the additional content that you get access to, and you will be intrigued and tempted to join the full Patreon. But at the same time, I would rather have you be free than just not following our content at all. Now, I want to celebrate some of our recent subscribers. Thanks to Chris Vincent, Simon Oliphant, Dan Miller, Bill Vass, Mason Hall, Mutt, Colin Jones, Jeff Henderson, Iron Owl, Drudy, 1x4x9, and Rutch Gadsden. Join the club at patreon.com/universetoday. Old Uncle Bob, if gravity is such a weak force, then how does it factor at such enormous distances? Of all of the forces that we know of, yeah, gravity is the weakest force at the smallest scales. So if you have, say, the gravitational force of an entire planet, and you've got a magnet that is attached to your refrigerator, the magnet is able to hold stronger than the entire gravitational force of planet Earth. But over the longest distances, gravity takes over. So things like the electromagnetic force, strong force, the weak force, they drop more quickly than gravity does. And so when you have the mass of an entire galaxy cluster, it can reach out across tens of millions of light years. I guess, you are being affected by the gravity of the entire observable universe right now. And I guess you are theoretically being affected by the electromagnetic force of the entire universe as well. It's just that the strength of that field is very weak compared to the strength of the gravitational field. So up close, electromagnetism is stronger, but at greater distances, then gravity starts to take over. Lily Rose, what is the coldest place in the universe? So like, unless we discover some kind of alien scientific lab, the coldest place in the universe is here on Earth. I mean, there are labs that are bringing material down to just an insignificant fraction above absolute zero. And there's no way for you to get that level of coldness out in space just naturally. Instead, you know, the background temperature of the universe is around, what, 3 degrees Kelvin, 4 degrees Kelvin? So very cold, but not absolute zero cold. But there are places in the universe that are unnaturally cold, that are colder than you would expect. So an example of this is the Boomerang Nebula, which is estimated to have a temperature of 1 Kelvin. So it is cooler than the background temperature of the universe. And I actually don't know why the Boomerang Nebula is the coldest place in the universe. And I don't think scientists know why either. Like, obviously some mechanism is extracting heat from the system through outflows of gas or something like that. Phineas 994, what is your favorite thing to cover at the moment? So I describe this thing of like, what is my favorite thing to cover at the moment? These are my obsessions. And I generally have a few things that I am obsessed with at any point. And then I reach out to people, I do a bunch of interviews, and I sort of satisfy that curiosity and that obsession. And then I move on to another thing. And so when I'm looking through all of the big stories that are coming out, all of the press releases, all of the conferences, all of the trade papers, all of the research journals and so on, and I see one, it will strike my fancy. It will be like, I have questions. I'm curious about this topic in general. And it just comes and it goes. I will have several obsessions at any time. And then as soon as I've done enough interviews that I'm kind of bored of the question, then I will move on to some other obsession. And they are inevitable. They are relentless. They always show up. So right now, there's a bunch. So one is that we are right now just a couple of years away from everybody throwing everything at the south pole of the moon. And there's going to be a lot of landers. There's going to be obviously human missions, both from the Americans as well as the Chinese. There's going to be a lot. And yet there are a lot of questions that I have about various practicalities, about like, where's the water going to come from and how much water do we need? And how will we grow food and this kind of stuff? If we're going to really truly have some sort of long-term permanent base on the moon, not people living there forever, but just like a scientific research station, what are the intricacies of that? And so I've done a bunch of interviews relating to that. There's one that I just did where someone did the estimates about all of the water use and how much water is needed for agriculture and how much water is needed for drinking and how much water is needed for industrial processes like coolant for supercomputers and things like that on the moon and on Mars and places like that. So right now I'm quite interested in the practicalities of long-term exploration of places like the moon and Mars. I'm also really interested in how artificial intelligence, large language models can be, transformers, have applications in astronomy and physics and things like that. That, if you go and take every single picture of a galaxy that's ever been taken and you feed it into a transformer, will it generate accurate images of what galaxies are supposed to look like? If you have only part of a galaxy and then you show it, and then can it guess the rest of the galaxy? And where that's really interesting is you think about some of the images of the galaxies that we see early on in the universe. They're just these little smudges, but is there a way for us to understand what that little smudge is? So I think that there are a lot of really interesting discoveries that can be made by artificial intelligence when you just have enormous amounts of data, and astronomy is one of these ones. So I'm really interested in that right now, and you're probably going to see a bunch of interviews on that subject. And then often it's I don't know what I'm going to be interested in. What's my favorite thing to cover? It sort of happens after the fact, where I see some topic that I'm interested in. I reach out to the to the researcher, I conduct an interview, and then I walk away with more questions than I had in the beginning. And I'm like stunned that there's suddenly this whole new area, this field that I just didn't even understand was there. And now I'm completely obsessed with it. And then the cycle continues. So I have never, 25 years of doing this, I can count on this process occurring over and over again, that I will. And all I know is that what feels good for me as a creator, as a journalist, is to follow that instinct, to follow my curiosity. You know, I know it kind of drives Anton a little crazy because, you know, he's got these great ideas for episodes that could do really well and they could go viral. And we know there's a lot of interest in this topic. And I'm just not curious about it right now. I just don't care. And so instead, we have these like really in the weeds interviews with people who are working on various telescopes, because that's what I'm obsessed with. So what my favorite thing to cover is like what I'm curious about right now, and that will change within a couple of days, I'm sure. Ken Porter, why is space so black with all the suns and things out there? So this is an extremely profound question, and this is something that philosophers had been thinking about for a long time, and the name for this is called Olber's paradox. And so when you think about it, like if we live in a universe that is infinite in all directions and timeless, that lasts for an infinite amount of time, it's always been here, then in whatever direction that you look, there should be a star somewhere in that field, you know, at that exact point. Now, it might be close, it might be far, it doesn't matter, because eventually, if it's infinity, there's going to be a star there. And so the night sky should look white. It should look like the color of all of the stars of the universe. But when you look out into the sky, we don't see all of the stars in the universe. We see darkness, and then we see occasional pinpoints of light, which are the stars. And so why is this? And the answer is, like, when we went back to that first two things that I said, that the universe is infinite. Yeah, it probably is infinite. It might not be infinite, but it's essentially infinite. But it also has to be timeless. And it's not timeless. That the universe has a finite age. It is 13.8 billion years old. And so when you look out into the universe in any one direction, you're only seeing to a maximum of 13.8 billion years in time. And that there is still more blank space in the regions in between those stars than there are light. And so this is why we don't see a sky that is bright, the color of a star. We actually see darkness. And then the other aspect of this is that this color of the light that is reaching our eyes has been redshifted to a region of the spectrum that we can't see. So if you could see in the microwave, then you would see light in all directions. You would see the color of the sky, which is essentially a time when the entire universe suddenly became transparent and light was able to escape. It's, you know, back at that time, about 380,000 years after the Big Bang, it was like a dull red color in all directions. But then over time, that light has been redshifted to the point that it's now in the microwave spectrum. We can't see in the microwave without special instruments, and so we can't see it. And so the light that is everywhere, we can't see with our eyes. MC Hall, has JWST just broken everything we thought we knew about the early universe? What's the wildest thing that JWST observed that we can't explain? No, I would say that JWST has not broken all of our expectations about the universe. It has nicely filled in a lot of the questions that astronomers had about the early universe. What were the masses of the various galaxies that were coming together? When did the quasars start to turn on? How heavy were the supermassive black holes that were seen in the early universe? What were the constituent elements of the galaxies as they were starting to piece together to become the larger galaxies? I think there have been some surprising discoveries of galaxies that seem to be a lot larger. You know, the distribution of galaxies from tiny galaxies to big galaxies, there are more bigger galaxies than astronomers were expecting. But there's this survivorship bias. There's like the bright galaxies are the ones that you can see. The big galaxies are the ones that you can see. You can't easily see the ones that are very faint. And so, you know, we still don't have the instruments that are capable of doing a better, more proper distribution of exactly all of the galaxies that we're seeing. And I think astronomers are genuinely surprised and impressed to see that there were very massive galaxies forming very early on, that there were supermassive black holes that were forming very quickly with, in some cases, like 1 billion times the mass of the sun, and yet still less than 1 billion years after the Big Bang, and that these quasars are starting to form. But nothing is completely outside their expectations for what we should see in the early universe. And now we're just going to see continuing refinements and just like generations of entirely new questions that are going to jump on top of that. Kenneth, is the Great Attractor moving away from us? Yes. So the Great Attractor is this name that was coined when astronomers were measuring the motions of galaxies that were above and below the galactic plane. And so when you sort of look out in the universe, you see all these galaxies moving away from us, but for a weird reason, when you looked at the ones that are just above the galactic plane and below the galactic plane, they seem to be moving, I mean, they are moving away from us, but they're also moving sort of in relation to some hidden mass that is on the other side of the Milky Way. And the problem is that the center of the Milky Way is filled with gas and dust, and so you can't make visual astronomy observations through the center of the galaxy. And astronomers call this the zone of avoidance. And, you know, I like to call this like the zone of don't bother. Like your telescope isn't going to be able to see through it, so just don't bother. But that said, in the last few decades, astronomers have revolutionized astronomy using infrared and other wavelengths. And with infrared, you can actually peer through the gas and dust and be able to resolve the galaxies that make up the Great Attractor. And so for the longest time was this big mystery. Like, what could it be that all these galaxies are being pulled towards something? Well, it's the gravity of a bunch of galaxies that are on the other side of the Milky Way. And they happen to be, you know, from our perspective, we can't see them. Right? There are parts of the sky that we can't see, and this happens to have a large, massive object on the other side. But now astronomers have mapped out most of the Great Attractor. They can actually see all of those galaxies right through the Milky Way, which is quite impressive. So it's not that mysterious. But the Great Attractor itself is this giant cluster of galaxies that is moving through space, and we are affected by its gravity, but we're not being sort of sucked into the Great Attractor. You've just got all these galaxies that are being affected by this cluster of galaxies. And the Great Attractor itself is actually moving towards the Shapley supercluster, which is another supercluster in space that we can see out in the cosmos. And that's sort of its generalized direction of motion as it's sort of pulling or affecting these other galaxies that are sliding towards it through space. John Doherty, if Starship was fully functioning, what would you want to see first? Well, Starship is a method of transportation. And so, you know, I personally wouldn't get on a Starship. I'm not sure we're ready for human beings to step on a Starship and fly to space on it. But I think the first thing that we want to see is we want to see payloads go to space. We want to see refueling rockets and lunar landers going off to the moon. We want to see giant telescopes put into space on the largest rocket ever built. We want to see the costs come down for the kinds of missions that have been waiting for a cheaper way to be able to get to space. There are a lot of amazing mission ideas that have had to be shelved because they were too heavy, they were too large, they were too complicated. Well, if you have a rocket that can carry more than 100 tons to orbit, it's got a cavernous 9-meter fairing, you can fit a lot of heavy telescope, inexpensively into a Starship, and you can launch it into space. So I don't really care about sending people to the moon or sending people to Mars. You know, I think that's going to happen inevitably. And you don't need a gigantic launch system to be able to do that. What I'm really mostly excited about is the potential for really cool missions to be able to fly for a fraction of the price. And so that's why I'm rooting for Starship. Like, I really want that thing to fly. I want it to work. I want it to be a fully reusable 2-stage rocket that at least is safe for inorganic payloads, for robotic payloads, to be able to provide us that next generation of space telescopes and missions that can explore other worlds. All right, those are all the questions that we had this week. Thank you, everyone who asked questions in the YouTube comments, and thanks to everybody who joined me for the live show. Now, we record this show live every Monday at 5 p.m. Pacific, right here on the YouTube channel. So you should see a notification for where the next channel is. Subscribe, click on the notification bell. I promise YouTube will tell you when it's going to go live, but it'll be 5 p.m. Pacific right here on this channel on Mondays. All right. we're going to continue on with the book club. I'm going to give you a review for another book that I read. But first, I'd like to thank our patrons. Thanks to Abe Kingston, David Gilton, David Matz, Dennis Alberti, Dustin Cable, Jeremy Matter, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Roebuck, Stephen Krasaki, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. All right, so I gave you a book review last week, and I gave you another book review this week. And so this week, the book that I read is Demon by Daniel Suarez. And this is a book that came out about almost 20 years ago. And the gist of the book is that a very rich programmer dies and unleashes an artificial intelligence demon onto the internet, which is then going out to seek revenge on his enemies and maybe try to subjugate humanity. And the story is told from a bunch of different perspectives, people who are aligned with the artificial intelligence and people who are trying to stop the artificial intelligence. And what makes the book amazing is how plausible and kind of terrifying trying to stop an artificial intelligence could be if it was trying to cause mayhem, because it's everywhere. It can start developing technology. It can start hiring human beings to carry out its wishes. It can hide in all these different places and isn't super concerned about its own safety and can turn cars into missiles. And so while you're reading this, you're kind of like, oh, that's kind of scary. That's a really good idea. And then you sort of realize that, things could be a lot worse, that this is just like the very beginning of what could be possible if we have like a very awful rogue artificial intelligence. So I enjoyed the book. I enjoyed the creativity of sort of like what was possible. And then at the same time, I felt like it didn't go far enough, that things could get even worse and even more horrible and even more arcane and surprising. And I think Daniel's imagination sort of tapped out at what would make a good movie, I guess. But I enjoyed the book. I really liked it, and sort of a good, serious thought at what are we like if the AI uprising happens. So Demon by Daniel Suarez. Check that book out. All right, so if you've got book recommendations for me, we'll put a link to the book club down below. You can go there and just recommend books. I'll read them and I'll tell you what I thought. All right, we'll see you next week.